increment in the length due to thermal effects, that is heat. When there is expansion in length in one dimension, we call it as thermal linear expansion. If the area increases, if the area of the body increases, we call it as superficial expansion. And if the volume of the body increases, we call it as cubical expansion. So these are the expansion that we did. Now, between their coefficients, coefficient of linear expansion was alpha, coefficient of superficial expansion was beta, and coefficient of cubical expansion was gamma. So there is a relation between all these three. That derivation you do not need to do, though it's written over here. This is the relation which you should remember. Gamma is equal to 3 alpha, alpha is equal to gamma by 3, and beta is equal to alpha by 2. Just in case if it is required by you, then you can use it. So do one thing, note down these steps. No need to mark it as important for your exam. Very least chances are there that this derivation, just mention these. And if you want, you can note down this. Then we'll move on to applications of thermal expansion. Now, see, you do not have to do all the applications in very much detail. We'll just see briefly. And in one of the applications, we have the usage of calculation part that I'll tell you. So applications of thermal expansion of solid, these are very, very basic. If a question comes, the theoretical question comes where you have to mention what are the applications of thermal expansion. So all the three types we had seen, linear, superficial, cubical, or volume, you can say. So one, I'm reading it out. Any doubts you have, you can ask me. These are very, very basic types of applications. So while laying the railway tracks, a small gap is left between the successive lengths of the rails. Now, why is it left? What did we study? Because of heat, thermal expansion occurs. Expansion of solids occurs. So here, if the railway tracks are kept, if the railway tracks are laid down, when the train will move, whatever heat will be produced due to friction between the tires and the railway tracks, that heat will expand it. So that's where a small gap is left so that it can expand. Secondly, when the iron tire is to be put on a wheel, the tire is made slightly smaller in diameter than that of the wheel. Same thing when the vehicle will be moving, there will be friction produced by the vehicle, and that friction will be causing heat, and that heat is responsible for expansion. So to let the gap for expansion, there is always a gap already maintained. In bridges, one end is rigidly fastened to its abutment while the other rests on the roller. Same thing, because see, when bridges, one end is fastened because it will expand, and one end rests on the roller. Second is that the fact that a solid expands on heating and contracts on cooling is utilized in diverting. What is meant by this? Whenever you have to fix something, you must have seen this also in your daily lives also. when something has to be fixed, something has to be riveted, a screw has to be fixed, two things that are made up of metals or iron, these have to be fixed. So what is done? They are heated and suddenly they are cooled. Then they are heated, then they are cooled. This alternate cooling and heating causes riveting. So that is also one of the applications. One application is in time period of pendulum. See what happens. The pendulum clocks that are present, these pendulum clocks, these have a metal bob attached with the help of spring. So as 1 hour is completed, this shifts. Then again 1 hour is completed, this shifts. 1 hour is completed, this shifts. So how does the pendulum know that 1 hour has been completed? Pendulum is just a clock. How does the pendulum recognize the fact that yes, this is moving? So as soon as this completes one oscillation, it recognizes that 1 minute is over. So 60 oscillations, 1 hour. Like this, the pendulum clocks work. So same thing, if heat is there, no, this length of the pendulum clock can increase if it is made up of proper metallic solids. So that can also expand. So if it expands, if length increases, time will decrease. Time will decrease in the sense, now what will happen? Length is increasing. Oh, sorry, time will also increase. Look here. This is a relation you must have heard already. T is equal to 2 pi under root L by G. Now, time period is directly proportional to length. So if somehow because of heat, the length has increased, so the time will also increase, right? So time increment in the time means what? How can time increase? Time is a definite quantity. Time is fixed. But what is being referred here is that now since the length is greater than the usual, this will complete the oscillation faster. So what actually has been passed as 3 seconds would actually have been 5 seconds in your clock. This will show you time a little faster. And same thing, if somehow it is cooled up and the length decreases, so time will also decrease. You'll get a very small amount of time for the actual time that is occurring. So this is one of the applications. Then there's derivation calculation part you do not have to perform. Do one thing, note that part down, then I'll tell you rest of it. Just note down this and remember the time length relationship. Done till here?
Yes, ma'am.
Okay. See now rest of the application. So this is very simple. This is just based on this fact. See, length and time are directly proportional. Why am I not doing this in detail? Because that is not a part of your syllabus, and this derivation is also not there. T is equal to 2 pi under root L by 3. This is part of waves and SHM. That time we'll see. So one of the applications was this time period of pendulum. So this doesn't mean in reality the time is changing. It's that the clock will show you a defective time. Then yes, this is it. A change in the reading of meter scale. So this is also very simple. You do not have to do this in detail because we have already done linear expansion and the questions on it. It is like if a scale, see, let's say this is a scale I've taken, or let me redraw it so that you will understand it better. Look here. This is a scale. Fine. So markings will also be there on the scale. Let's say this is 0, this is 1, this is 2, this is 3, this is 4. Fine. Now I have taken an object. Let's say I've taken this object, and how much this measures? This measures 4 units. Let's say 4 centimeters or something. 4 units. Now I have heated this metallic scale. This is not a plastic scale. I have heated this metallic scale. Now what is happening? On heating the metallic scale will expand. Linear expansion we have already studied. Let's say scale expanded. Fine. Now look at the readings of it. Let's say this expanded. The 0 that was here is here. Now since it has expanded, 1 will go here, 2 will go here, 3 will go, and so on. Like this, the scale will go. So now if I'll measure, see, earlier this was coming exactly 4 centimeter. Right, on this scale, it was coming exactly 4 centimeter. But now look, this is the same object. This is around 1.2 centimeters. See the difference. So if any metallic scale is heated, on the meter scale is heated, you'll get improper reading. So there's a change in reading. So same thing. Now questions from this part will be exactly what we did in the last class. This. See, if temperature here is T1, here is T2, T2 is greater than T1, then you will use the same formula for temperature, no, for expansion in the length. This will be L0 1 plus alpha delta T, and delta T will be T2 minus T1. Same thing. This is the change in meter scale. So true reading will be true reading. This is now true reading. We write now the original length, true reading. Then by the original, I'll not write here. It's already written over here. True reading is equal to scale reading into 1 plus alpha delta. Whatever is the actual reading is equal to scale reading into 1 plus alpha delta. This is the change in the reading of meters. Note this down. Then we'll have 1 or 2 applications are left. One is for bimetallic strip and one more also. Okay, now, so this was change in the reading of the meter scale. Okay, yes, this is also one of the applications. C class, this is not so very important, but if question comes from the application part, so you have to mention the thermal expansion regarding the time also, you have to mention it regarding the scale also, the improper reading that occurs when you place an object. Then the cavity. See, if a very narrow cavity is drawn up, then questions are asked like this, that why does the cavity increase? Why does the cavity increase whenever you have heat provided to the cavity? So cavity basically increase, as I've told you, because of thermal expansion. So since now what type of expansion is occurring, that you have to identify. See, the length is not increasing. For the circle that is present within this, length is not increasing. What exactly is increasing? The area. So which type of thermal expansion it will be? It will be superficial expansion. So cavity increases whenever heat is provided. This is another theory part, bimetallic strip, C class. Then we'll do effect on density. This is important. Bimetallic strip is what? There are two strips. Fine. This is A, this is B, and I have connected these two strips. Now I have provided heat over here. Once I have provided heat, what I have noticed is that it turns like this. It turns in the form of C shape. The proper bimetallic strip which was kept, now this is in the form of C shape. Now, the question that comes is, how will you determine whether it's A over here or B over here? It could have happened, no? This is the, let's say, metallic strips. These are the metallic strips that have curved. This could have been A, this could have been B. Why is it the longer one is A and why is it the shorter one is B? Right. The main question is that why is the longer one A and shorter one B? Thing is that whichever has the more coefficient of linear expansion or any type of expansion, that will expand also more, because we have seen through the formula L is equal to L naught 1 plus alpha delta T. So if L is equal to L naught 1 plus alpha delta T, from here you can easily predict that length and alpha both are directly proportional. So in this case, in the bimetallic strip, it was mentioned that A and B, out of these, alpha 1 is greater than alpha 2. So if alpha 1 is greater than alpha 2, alpha 1 means A will have a greater length. Why? Because of this relation. This will be having greater length as in comparison to B. So that's why this curves like this. Both will curve, but A will be having a longer curve, longer curvature as compared to B. So how the questions will come in your exam, it can be asked to determine which one is both of them. Out of these, which one is A or which one is B. Lastly, you have effect on density. So this is the last effect from the thermal expansions. See here, density we have already done. Density we already know. Density is what? Mass by volume. Let's say this is density at temperature 1. Density at temperature 2, rho 2, this will become mass by volume 2. Volume will also change. And volumic expansion, we had seen that this was V1, 1 plus gamma delta T. Right. V2 is V1, 1 plus gamma delta T. So if I put in the value of V1 from here, if I put in the value of V1 from this equation, look what I'll get. This will become, this will be, or let me put the equation of V2. I have the value of V2, no, V1, 1 plus gamma delta T. Let me put in the value. So rho 2 will become M divided by V2. Now what is V2? V1 into 1 plus gamma delta T. V1 into 1 plus gamma delta T. Fine, V1 1 plus gamma delta T. So if you take up the ratio, M by V1 is what? Look here. This M by V1, this is directly density 1. So what do you get? You get a final relation, that is rho 2 is equal to rho 1, 1 plus gamma delta T. This is the relation that is used. And one thing remember, Whenever the density is decreasing, it means the temperature is increasing. So these are all the applications of thermal expansion. Now you are left with that heat part that we'll see. But one more thing, apparent expansion is also there, a very small topic that I'll discuss it. First, note down these points. Few points are there, note it down. Just these cavity part, this you have already written it, this cavity part from here. Aram, in your school, as you have already given the exam, so you must be aware of the thermal physics syllabus. So please just send me in the chat box right now here only what all topics have been deleted from this thermal physics unit. I think like in thermodynamics, you do not have refrigerator. Refrigerator entirely has been deleted. So whatever topics you remember, just please send me Aram right now if you remember it.
Ma'am, which chapter?
The thermal physics unit, mainly you have these thermal expansion, what we are doing, then thermodynamics and kinetic theory.
Okay. Ma'am,
Yes, Aram.
ma'am, I'm not sure about the topics which are deleted, but I can tell you the topics which are coming.
Yeah, you tell me that.
Okay, I'll read it out.
It's better if you can type it in the chat column.
Okay.
Okay. So this is from kinetic theory, no? All these topics. And do you know for these two as well, thermodynamics and thermal properties? If you have the topics, please send me. I just want to cross check it with what I have for this year. Okay.
Okay, I do have that.
Or you can do one thing also. Later on, you can send me on WhatsApp also if you are having to type so much no right now, because lots of topic you have to write. So it's better if you have the pic, you can send me on WhatsApp also.
Okay, I'll send you in WhatsApp.
Okay, thank you so much. Aaron. Thanks a lot. All right, class. Now see, for the expansions that we have, thermal expansion of liquids, this also you have to do in brief only. There is real expansion and apparent expansion. Now, what is meant by this? Real expansion and apparent expansion. See, if I take up a glass, I have this glass, and I have filled this glass entirely with water. So lots and lots of water is accommodated in the glass. But if I remove or replace the glass with a huge bucket, let's say I have taken the bucket. So what will happen to the amount of water? Amount of water will still remain the same, let's say somewhere till here at this level. So this entirely, which was filling up the glass, was looking as if it was completely filled. Now, as soon as this water is poured into the bucket, this is appearing as if this is just single layer. Right. So what is happening? Same thing is here. If you take up a container and you fill it with some sort of liquid, let's say water, any liquid you have taken, and you have filled it, and now you supply heat. So when you supply now heat, what will happen? When the container will expand, water will decrease. When the container will expand, water here it will decrease. So this is known as real expansion and apparent expansion. There is one case where liquid expands, and there is one case when container is expanding. So when the actual liquid is expanding, no, I'll give you an example. Milk, you have seen boiling of milk. When you boil the milk, what happens after some time? Do you see the milk rises up? It expands. So is it the container that is expanding or the real liquid? It's actually the milk that is expanding. So we call it as real expansion. Let's say this was the initial volume of milk. After certain temperature, when the temperature is increased, a certain amount of heat is given. This increases and rises such that we have to switch it off, right? When we boil the milk. So this is real expansion. But if let's say if the volume, the quantity of volume is not changing, if you are saying the container is expanding, so that is known as apparent expansion. That will look like as if the liquid is also expanding along with it, but in reality it is just the container expanding. So you will always have real expansion greater than apparent expansion. Why? Because in your real expansion, the actual volume of the liquid was expanding. Right now, what is happening? Right now, only the container is expanding. So whatever volume was initially kept, it is still the same. So that is what is the difference between real expansion and apparent expansion. And you have a relation also. You have a relation between them. See, when the real volume is greater, real expansion of the real volume is greater than the volume of container. So liquid's level will increase, right? Liquid's level will keep on increasing. Example was the milk example. If container is more, level of liquid will decrease. Example, that glass and the bucket one. When it was a small container, when it was simply a glass, liquid looked completely filled. It was too much to accommodate. But as soon as the glass expanded in the form of bucket, it became as the size of a bucket. The liquid level simply became unilayered. So that means if volume of the container is more, the change in the volume of container is more than the real volume of the fluid, level of liquid will decrease. And if both are same, nothing is happening. Level of the liquid will remain as it is. It will remain the same. Level of liquid will not change. So you have few relations. These relations also you have to do just brief. Real increase in volume of liquid per unit original volume degree rise in temperature is the coefficient of real expansion. Coefficient of real expansion is real increase in volume. Real increase in volume means delta V, actual increment in the volume per unit original volume, per unit original volume that is present, per degree rise in temperature delta T. So real increase in volume of the liquid per original volume degree rise in the temperature. This is coefficient of real expansion. And if you have to write coefficient of apparent expansion, and remember class, we are using the symbol gamma. Why gamma? Because here you just have cubical expansion, volume is getting expanded. So this gamma apparent is apparent increase in volume. This is apparent increase in volume by original volume into delta T. That is how we write. Okay, note down these points for expansions of liquid. All we did yesterday was thermal expansion of solids. Right now we are doing thermal expansions of liquid. Okay, now see, next we have as specific heat capacity. So thermal expansion was of solids was different and liquids was separate. So anomalous properties of water that you don't have to do. Simply we'll do specific heat capacity. Now see, specific heat of a solid or liquid. This is defined as whatever is the amount of heat that is required to raise the temperature of 1 kg by 1 degree Celsius. This means that whatever is the amount, whatever is the mass given for 1 kg, whatever is the heat that is supplied. So whatever heat will be directly proportional to the mass. And this heat will also be directly proportional to the temperature difference. So initially there is always one temperature and there is a final temperature. So the temperature difference that is present, delta T, the way we had seen on case of thermal expansion. So same thing is here also. Delta Q is directly proportional to delta T. So heat change is directly proportional to mass. Heat change is directly proportional to temperature. Let me combine these two. What do I get? Delta Q is directly proportional to M delta T, right? M is mass, delta T is temperature. So here when I'll remove the proportionality sign, I'll put in a constant, and that constant is known as specific heat capacity. The way now we had alpha, alpha was coefficient of linear expansion, gamma was coefficient of superficial expansion. Then, sorry, beta was coefficient of superficial expansion. Gamma was simply coefficient of cubical expansion. So same way here also, the constant that will come here, delta Q, this will be equal to Cm delta T. So this is the entire formula that we get. Delta Q is equal to Mc delta T. Everywhere we will be using Mc delta T. What is C over here? Specific heat capacity. Fine. So specific heat of a solid, you talk about solid or a liquid, this is defined as amount of heat required to raise temperature of 1 kg of solid or even liquid through 1 degree Celsius. Or you can take 1 Kelvin as well. SI unit of temperature is Kelvin. So you can take 1 Kelvin also. Why am I saying this? See, if in this formula I'll put mass, let me write the value of C. C can be written as delta Q divided by M delta T. Now, delta Q is what? Delta Q is the heat, amount of heat. Let's say this is 1 joules. Or let's not even equate this. Let's leave joules as it is. Let's see this. M is mass. If I put mass as 1 kg and temperature as 1 Kelvin, what do I get? C is exactly equal to heat. So C is that is the specific heat capacity. This is the uh, amount of heat for 1 kg of solid per Kelvin. Fine. Note down this part, then I'll tell you more. What all how we have to do in this. One more thing, class, I forgot to tell you the SI unit. See, if you'll write C over here, that is the specific heat, specific heat capacity. See here, SI unit of heat is joules, SI unit of mass is kg, and SI unit of temperature is Kelvin. So joules per kg per Kelvin. That is the SI unit of it. And if you want to write out the CGS unit, this is the SI unit. And if you want to write the CGS unit, see, just convert it. Joules will become calorie, kg will become gram, and this will become per degree Celsius, per degree Celsius. Now see what has been written over here is, this is a mass, this is a block of mass M, and initially we are having here T1, at the end we are having T2. So there's a temperature difference in the body, right? Temperature difference is T2 minus T1. So that is only what I have written, delta T. And delta Q is what? It's the amount of heat provided to the body. When we increased the temperature from T1 to T2, the heat also increased. Fine. Now note it down. And as you've done, let me know. We'll practice one very small question from this. Questions are easy from this part. Very easy. One-liner. See class, here you had to calculate the heat required to raise the temperature of 10 kg of water. So what's the temperature difference over here? Initial temperature is 10 degrees Celsius, final temperature is 50 degrees Celsius. So change in temperature is 40 degrees Celsius and specific heat capacity, this is given as 4.2 into 10 to the power 3. Now see class, in this question, this is provided. In most of the questions, specific heat capacity for water won't be provided. So 4.2 into 10 to the power 3, this you have to learn by yourself. Now when you'll put in the formula, change in the heat, this is equal to what? MC delta T. What's the change in temperature? Final temperature minus initial temperature. You get 40 degrees Celsius. Now mass is 10 kg, specific heat is 4.2 into 10 to the power 3, change in temperature is 40. So final answer